Okay, in this presentation we're going to look at things like the probability generating function and the moment generating function of discrete random variables. In this instance, what we're asked to do is show that the probability generating function for a binomial distribution with parameters n and p is given as follows. G of x t equals 1 minus p plus pt to the power all to the power of n, okay, all n in brackets, and deduce the moment generating function from that. So there's two key definitions for both parts of the question. The first part is the probability generating function, and down below we have the moment generating function down here. Okay, so essentially what we have to do here is it's essentially treating it as a discrete random variable. Okay, z to the power of x. The expected value is z to the power of x. Actually, I'll just sort of, because we're working in terms of t up there, I'll just change that to t. That's just the notes, essentially. But just to make life easy on ourselves, it is the expected value of t to the power of x. Okay? Probability of x by t to the power of x. Okay? So essentially we're going to just treat it like a discrete random variable with just a bit of a twist. Okay, so there it is. The PGF is the expected value of t to the power of x. So here we have t to the power of x, and the probability of x equals each particular value there. Okay, so what we're going to do here is actually just split it up into two. Here we have t to the power of x, and this is the probability mass function for a binomial distribution here. So this is where this comes down from here. Okay, so we're actually going to sort of split it out and use the probability mass function for a binomial random variable. Now the thing is here that we can sort of try and tidy things up as much as possible. So here we have t to the power of x and p to the power of x. So t to the power of x times p to the power of x is essentially, we can rewrite that as pt to the power of x. So that's where we got there. And that is, we have n minus p to times n minus x there. And we have the binomial coefficient there. And there we use the binomial theorem to re-express it as that. Okay, so that's the binomial formula there. Okay, now the thing is, this sort of stuff pops up a lot, particularly in these sort of definitions relating to the binomial distribution. So just almost expect this to come up somewhere. You should, like when you're doing this sort of level of mathematics and statistics, stuff like the binomial formulas, that comes into play quite a lot. So just be prepared to use them. Okay, so essentially this is how we go from pt times n 1 minus p, sorry, p t to the power of x times 1 minus p to the power n minus x. That's how we sort of go. We use this formula here just to get to here. Okay, and that's how we end up down here. So essentially, the key thing there really is, apart from the definitions, is just sort of anticipating the binomial expansion there, that binomial distribution or binomial theorem. Now, we're asked also for the moment generating function, the MGF, and that's a very straightforward job in this instance. Essentially, what we have to do here is, in this instance, we're asked to find the expected value of t to the power of x. Here we're just asked for the expected value of et to the power of x. Okay? E to the power of t to the power of x. So essentially what we can do there is just replace t by e to the power of t, and that's the job done. In that instance, that's actually very straightforward substitution. So that's it. That is the binomial distribution and how to calculate the probability generating function and the moment generating function. We'll leave it there.